Hey everyone, my name is Taylor Sparks. I'm the editor-in-chief of Integrating Materials and Manufacturing Innovation. And in today's paper, we're talking about a new tool for getting data out of literature. Now, there's been a couple of these lately. This is a hot topic right now in material science as these large language models have emerged with surprising capability to get data out of the literature. In this paper, they're going to talk about that, but specifically, they're going to cover this concept of expert grounded automatic prompt engineering. I'll describe what that is in a moment. This work comes to us from lead author Shunshun, corresponding author Prasanna Balachandran. It's a collaborative work between University of Virginia and Penn State University. Okay, they start out by saying, like we've all seen, that there's been this explosion of using LLMs for getting data out of literature. They seem really good at this. But they do point out that while they can have reasonable accuracy, the performance depends critically on the prompt quality, right? That's huge. And I've seen that in our own research published in IMMI. In this paper from 2 years ago, we did structured prompts, right? Basically a way of introducing examples in the prompt itself of what you're looking for. And this played a huge role in reducing the amount of training data needed. They're going to build on these concepts, right? They point out here that the prompt itself typically has 4 elements. You've got the instructions, right, where you're telling it the task and your behavior. You provide the context, so relevant background information, then the input data to be processed, and then 4, you've got this output indicator specifying the format and the structure of the response. So what are they going to do? They're going to leverage that content in the prompt to figure out what should be the best thing to go into there. And it's pretty clever. It says here, we develop an expert grounded automatic prompt optimization framework for extracting experimentally measured room temperature lattice constant data from thousands of HEA publications. So they're going to focus specifically on one subgroup of material science, right? HEAs, and of that, just the lattice parameter. So it is a pretty narrow thing they're asking it to do. But what's clever here is this approach about the automatic prompt optimization. Okay, figure 1 here is maybe the best place to explain it. First off, they're using something called TextGrad, right? TextGrad is a tool that allows you to convert text into a gradient. Basically, by comparing things, you can get a difference, you can calculate a gradient. So it allows us to compare text and then through the language model actually figure out how to make slight changes to get it to match something using gradient descent. Cool approach. They're going to leverage that here. So the idea is they will do some manual annotation, right? They're going to take literature and they're going to come up with manually labeled data, okay? But then here's where it gets cool. They don't have to know the right prompt. Instead, they have in step 2 here, module 2, they've got this multimodal LLM, which is going to generate a prompt, okay? And then from that prompt, it's going to actually extract the data. And then when it takes the extracted data and the manually labeled data with very limited examples, only like 7 actually labeled examples, it's able to compute a loss using this TextGrad framework and use that to then, via the backward engine, update the prompt, run this again, try to do the extraction again, and try and match the prompt. Isn't that clever? Sorry, they're trying to match the output by iteratively learning the prompt. I think that's really cool. And then ultimately, once you're satisfied, when you've reached a cutoff criteria that you're happy with, then you send the final prompt forward. This purple line shows how they actually take this optimized prompt and do the final expert level data extraction. So does it work? Yeah, it seems to work. If you check out table 1 here, they're showing the initial prompt on the left. You've got precision recall F1, and then the optimized prompt, precision recall F1. Check it out. The initial prompt has great precision, but its recall is awful, right? There's a bunch of things it should have captured that it's not grabbing. But the optimized prompt, you don't really lose much in terms of precision, but your recall is dramatically better. You're going from 0.27 to almost 0.9. It's a phenomenal improvement. You can see this in example of the data. Like here's where they've actually employed this tool. They looked at 2,267 publications. This was over many different HEA alloy families, like 1,800 of them. And you can see that, you had this problem with lots and lots of entries where they're just missing it, right? And then even when it does have it, you have to do the extraction. So they're able to show that this tool works pretty effectively actually to increasing the recall of this data extraction of this very specific materials challenge. I appreciate that they put together this table here where they talk about when things go wrong, like how can they go wrong. Obviously, these are language models, they can still hallucinate. So for example, it extracted a lattice constant, but it extracted from a precipitate phase, right? The LM didn't differentiate from precipitate to matrix and it made a mistake there. There will be semantic misinterpretation. This is interesting. It says the LM incorrectly identified Berger's vector as a lattice constant, right? Because it's a small number in the units of angstroms, but it didn't realize that was a lattice parameter, so it made that mistake. There's format and unit conversion errors. Like, for example, it didn't know how to interpret angstrom symbol sometimes. So these are the types of errors they saw. But overall, I think this is really an interesting approach. It's a clever idea to figure out, let gradient descent figure out what the best prompt should be to get output that matches what a human would deliver. Pretty cool. Ultimately, they showed that the workflow they did on Claude 3.5, Sonnet's model, and they bumped it from 2.7 up to over 90. And then they showed that it actually can be deployed on other smaller models as well, right? It enables deployment on lower cost architectures without reoptimization. They tried it on Gemini 2.5. So this is a cool approach. Obviously, this is super specific, but the benefit here is that you can then take the same approach, and for some other materials domain, if you have another specific extraction request, it would be relatively simple to apply this TextGrad framework here again and to re-update the prompt for that extraction. So I hope you'll read all about it in the latest issue of IMMI.